In mathematics, a Diophantine equation is a polynomial equation in two or more unknowns such that only the integer solutions are searched or studied. A linear Diophantine equation is an equation between two sums of monomials of degree 0 or 1. An exponential Diophantine equation is one in which exponents on terms can be unknowns. Diophantine problems have fewer equations than unknown variables and involve finding integers that work correctly for all equations. In more technical language, they define an algebraic curve, algebraic surface, or more general object, and ask about the lattice points on it. The word Diophantine refers to the Hellenistic mathematician of the 3rd century, Diophantus of Alexandria, who made a study of such equations and was one of the first mathematicians to introduce symbolism into algebra. The mathematical study of Diophantine problems that Diophantus initiated is now called Diophantine analysis. While individual equations present a kind of puzzle and have been considered throughout history, the formulation of general theories of Diophantine equations was an achievement of the 20th century. Examples: in the following Diophantine equations, x, y, and z are the unknowns and the other letters are given constants. Linear Diophantine equations. One equation, the simplest linear Diophantine equation takes the form x plus by equals c, where a, b and c are given integers. The solutions are completely described by the following theorem: this Diophantine equation has a solution if and only if c is a multiple of the greatest common divisor of a and b. Moreover, if is a solution, then the other solutions have the form, where k is an arbitrary integer, and u and v are the quotients of a and b by the greatest common divisor of a and b. Proof: if d is this greatest common divisor, Bar-Copyright-Zout's identity asserts the existence of integers e and f such that d plus bf equals d. If c is a multiple of d, then c equals dh for some integer h, and is a solution. On the other hand, for every integers x and y, the greatest common divisor d of a and b divides x plus by. Thus, if the equation has a solution, then c must be a multiple of d. If a equals ud and b equals vd, then for every solution, we have, showing that is another solution. Finally, given two solutions such that x1 plus by 1 equals x2 plus by 2 equals c, one deduces that u plus v equals 0. As u and v are coprime, Euclid's lemma shows that there exists an integer k such that x2, x1 equals kv and y2, y1 equals q. Therefore x2 equals x1 plus kv and y2 equals y1, kv, which completes the proof. Chinese remainder theorem. The Chinese remainder theorem describes an important class of linear Diophantine systems of equations. Let n1, nkbk pairwise coprime integers greater than 1, a1. Arc bk arbitrary integers, and n be the product n1 The Chinese remainder theorem asserts that the following linear Diophantine system has exactly one solution such that 0 a per-mole currency x, n, and that the other solutions are obtained by adding to x a multiple of n. System of linear Diophantine equations. More generally, every system of linear Diophantine equations may be solved by computing the Smith normal form of its matrix, in a way that is similar to the use of the reduced row echelon form to solve a system of linear equations over a field. Using matrix notation, every system of linear Diophantine equations may be written where A is a ma, n matrix of integers, X is an a, one-column matrix of unknowns and C is a ma, one-column matrix of integers. The computation of the Smith normal form of A provides two unimodular matrices U and V of respective dimensions ma, m and na, n, such that the matrix is such that B, I is not 0 for I not greater than some integer k, and all the other entries are 0. The system to be solved may thus be rewritten as calling E the entries of and D those of this leads to the system, B, i.e. equals D for 1 a per-mole currency I a per-mole currency k, 0 E equals D for k, I a per-mole currency n. This system is equivalent to the given one in the following sense: a column matrix of integers X is a solution of the given system if and only if X equals Vy for some column matrix of integers Y such that by equals D. it follows that the system has a solution if and only if b, I divides d for I a permeable currency k and d equals 0 for I, k. If this condition is fulfilled, the solutions of the given system are where hk plus 1, hn are arbitrary integers. Diophantine analysis, typical questions. The questions asked in Diophantine analysis include, are there any solutions? Are there any solutions beyond some that are easily found by inspection? Are there finitely or infinitely many solutions? Can all solutions be found in theory? Can one in practice compute a full list of solutions? These traditional problems often lay unsolved for centuries, and mathematicians gradually came to understand their depth, rather than treat them as puzzles. Typical problem: the given information is that a father's age is 1 less than twice that of his son, and that the digits AB making up the father's age are reversed in the son's age. This leads to the equation 10a plus b equals 2 minus 1, thus 19b, 8 Aries equals 1. Inspection gives the result a equals 7, b equals 3, and thus AB equals 73 years and BA equals 37 years. One may easily show that there is not any other solution with A and B positive integers less than October 17th and 18th centuries. In 1637, Pierre de Fermat scribbled on the margin of his copy of Arithmetica, "It is impossible to separate a cube into 2 cubes, or a fourth power into 2 fourth powers, or in general, any power higher than the second into 2 like powers." Stated in more modern language, the equation n plus bn equals cn has no solutions for any n higher than 2. And then he wrote, "Intriguingly, I have discovered a truly marvelous proof of this proposition, which this margin is too narrow to contain." Such a proof eluded mathematicians for centuries, however, and as such his statement became famous as Fermat's last theorem. It wasn't until 1995 that it was proven by the British mathematician Andrew Wiles. In 1657, Fermat attempted to solve the Diophantine equation 61x2 plus 1 equals y2. The equation was eventually solved by Euler in the early 18th century, who also solved a number of other Diophantine equations. The smallest solution of this equation in positive integers is x equals 226,153,980, y equals 1,766,319,049. Hilbert's 10th problem. In 1900, in recognition of their depth, David Hilbert proposed the solvability of all Diophantine problems as the 10th of his celebrated problems. In 1970, a novel result in mathematical logic known as Matyášović's theorem settled the problem negatively. In general, Diophantine problems are unsolvable. Diophantine geometry, which is the application of techniques from algebraic geometry in this field, has continued to grow as a result. Since treating arbitrary equations is a dead end, attention turns to equations that also have a geometric meaning. The central idea of Diophantine geometry is that of a rational point, namely a solution to a polynomial equation or a system of polynomial equations, which is a vector in a prescribed field K, when K is not algebraically closed. Modern research, one of the few general approaches is through the Hasse principle. Infinite descent is the traditional method, and has been pushed a long way. The depth of the study of general Diophantine equations is shown by the characterization of Diophantine sets as equivalently described as recursively enumerable. In other words, the general problem of Diophantine analysis is blessed or cursed with universality, and in any case is not something that will be solved except by re-expressing it in other terms. The field of Diophantine approximation deals with the cases of Diophantine inequalities. Here variables are still supposed to be integral, but some coefficients may be irrational numbers, and the equality sign is replaced by upper and lower bounds. The most celebrated single question in the field, the conjecture known as Fermat's last theorem, was solved by Andrew Wiles but using tools from algebraic geometry developed during the last century rather than within number theory where the conjecture was originally formulated. Other major results, such as Falting's theorem, have disposed of old conjectures. Infinite Diophantine equations. An example of an infinite Diophantine equation is which can be expressed as, how many ways can a given integer n be written as the sum of a square plus twice a square plus thrice a square and so on. The number of ways this can be done for each n forms an integer sequence. Infinite Diophantine equations are related to theta functions and infinite-dimensional lattices. This equation always has a solution for any positive n. Compare this to, which does not always have a solution for positive n, exponential Diophantine equations. If a Diophantine equation has as an additional variable or variables occurring as exponents, it is an exponential Diophantine equation. One example is the Raman-Werner-Uranagel equation, 2na7 equals x2. A general theory for such equations is not available. Particular cases such as Catalan's conjecture have been tackled. However, the majority are solved via ad hoc methods such as Starr-Mer's theorem or even trial and error. Notes. References: Mordell, L.J. Diophantine equations. Pure and Applied Mathematics 30. Academic Press. ISBN A0-12-506250-8. ZBLA 0188.34503. Schmidt, Wolfgang M. Diophantine Approximations and Diophantine Equations. Lecture Notes in Mathematics 1467. Berlin, Springer Verlag. ISBN A3-540-54058-X. ZBLA 0754.11020. Shorey, T.N. Schiederman, R. Exponential Diophantine Equations. Cambridge Tracts in Mathematics 87. Cambridge University Press. ISBN A0-521-26826-5. ZBLA 0606.10011. Smart, Nigel P. The Algorithmic Resolution of Diophantine Equations. London Mathematical Society Student Texts 41. Cambridge University Press. ISBN A0-521-64156-X. ZBLA 0907.11001. Stilwell, John. Mathematics and Its History. Springer Science Plus Business Media Incorporated. ISBN A0-387-95336-1. Further reading, Dixon, Leonard Eugene, 1920. History of the Theory of Numbers. Volume 2, Diophantine Analysis. Mineola, New York, Dover Publications. ISBN A978-0-486-44233-4. MRO 245500. ZBLA 1214.110020. External links, Diophantine equation. From MathWorld at Wolfram Research. Diophantine equation. From Planet Math. Haswinkel, Michiel, ed., Diophantine equations, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Dario Alpen's online calculator. Retrieved March 18, 2009.